Yes, you are.
Yeah. Okay. So I think we can start the webinar. People will join in between. We have already notified them. So let's start. So good morning, everyone. So welcome to Innovit Technologies live webinar on AIML. And here our goal is to make high quality AIML education accessible to everyone and equip learners with practical industry relevant skills that can drive innovation. And we are pleased to have Nishi Paul ma'am with us today. She's a data scientist at HP Enterprises and has previously worked with HSBC and MIQ with extensive experience across the domain like banking, financing, advertising, and IT. He'll be sharing the valuable insights on the real world impact of FAIML. So I thank you everyone for joining us today, and I hope we can start now. So today's topic will be AIML for Beginners Part 2, and with this we'll be also covering deep learning and few project implementations. Yeah, over to you, Nisha ma'am.
Thank you for the introduction. Good morning, everyone, and thank you for joining on a Sunday. So, I'll start sharing my screen. I hope my screen is visible.
Yes, it is.
Okay, thanks. So, today's topic is about the predictive modeling part 2, that is mostly around the deep learning. In the last webinar, we had a walkthrough over the machine learning, the important concepts about it, and today we are going to work over this deep learning. Now, deep learning concept is quite difficult. It has a lot of it has what is it? It has a lot of mathematics behind it. So if you are good with the derivatives, if you are good with the vectorizations, then it will be easier for you to understand what is actually happening under the hood. But if it comes to the coding part, then it's quite easy in comparison to the mathematics that is leading to this deep learning technology. Now, today I'm going to explain you the deep learning methods in the most simple term possible so that you at least understand what all the layers in the deep learning is talking about, what it means, and how, I mean, what the layers are trying to represent basically. And I haven't touched the mathematical background to it because that's quite difficult, and that requires hierarchical understanding. So let's move on. If you were in the previous webinar, you must have seen this equation, which is y equal to mx plus c. And this equation actually tells a lot. If you understand this equation, the basics would be clearer to you. So when we were doing it, we have gone through this weight term, which is the W, and we have gone through the bias. What this weight and bias does is basically aligning your output to the actual output. This y hat over here, this y cap, I'll just mark it here. Okay, I'll just mark it here. This is the output, basically y cap we say it. And now this y cap, we try to match the y, which is our actual output, to almost equal to this y cap. And this is done by the w and the b. Because you have this input of this x, and this x is having a definite value. You cannot change your input data. What you can change are the parameters that can align your input. Now, you may think that why do we have to know about this deep learning models if it is a Gen AI series? Well, when we will start with the LLMs, you need to fine tune it. And the fine tuning procedure demands the knowledge of Keras or this deep learning. You have to know about all the layers. You have to know about how this equation is actually performing all these actions. You need to know about how you can fine tune the dataset using the appropriate layers as needed. So if I give you this example, how it is working on, let's say you have this kind of a structure. I'm sorry for this figure, it's really very bad. So you have something like this, and these are your y labels that you already know. And this is somewhat like a line, and if you draw the line like this one, what is this intercept? This is the x-axis, and this is the y-axis. So this one intercept or the elevation from the zero is the bias term, and this slope is the parameter w. Okay, yes, exactly, y equal to mx plus c. So what this w and b is doing, it is basically aligning the line as per the data point. Now if you increase this w or maybe alter the w a bit in order to move it to the upward side, how it will become, let's say it will go somewhere right here and it might be more accurate than this line. So this is what this w and b is doing on your data. Now let's move further, since you already know about it and we have seen how it works. Okay, so in order to go through this deep learning procedure, I'm going to use some very basic examples and it's going to be quite easy. Okay, so you must have mixed colors, right? Whenever you were in, let's say school or college or something, you must have done some coloring, some paintings. It's a how you used to do it. You have some kind of this primary colors, this red and this orange, which is making up this pink, and then you're using this white color to make it more light or to keep it deep. So what were you actually doing? You were adjusting the proportions of the colors. So adjustment of these proportions is basically equivalent to the weights. So when we were talking about this equation, getting back to the previous slide, this W and B, I can draw an analogy that W might be the proportions and B might be this white color. So how we can put it, like these two parts of blue, four parts of orange. If we say this one, these two parts of blue, let's say this is a blue color, let's assume, and this four parts of orange is giving us a purple color. So what is the weight of the blue? The weight of blue is 2. The weight of the orange is 4, and that is giving us purple. Now this purple color is basically darker, but my demand is to get the purple color in a more lighter tone. So what I'm going to do is use the bias tone, which is the white. This is an analogy that you can think of, mixing of colors. Now when it comes to deep learning, there are a lot of weights, there are a lot of parameters, lot of biases will be there. In the previous equation, just as you have seen y equal to mx plus c, there is only just one m, one b, because there was one x. So as your feature increases, the number of weights will also increase. Just like over here, this red and orange, suppose this one's, this is a two part of red, let's say, this is a four part of orange, which is giving us this pink color. Now again over here there is a red and there is this purple or the blue, okay, that we are taking. So again, you need to change the weights assigned to it so that you can get the color of your choice. So as per your features, the weights are varying. This is one important thing to remember, that your weights will vary as per your output with the features. Okay. So this is what weight is. And I've done a bit of an explanation over here so that you can go through what it is actually. So weight is basically determining how your input is going to influence the Y or influence the output. So in this picture, if you go back, if you increase the proportion of this red a bit more, you might end up at some color which is more towards the red shade. That is not the thing you might want. You may want something like this blue, I mean the purple tone. So you have to increase this blue color. That is, you have to increase the effect of blue on this purple color. What you will do? You will increase the weight of it. So that is like you are balancing the weights of these input features so that you can get a proper output which will match to your expected output. Okay. And what is this bias term? As we said, bias is basically uh, shifting your model output. If we take the example of this line, it was aligning your model output line along with these data points. If it were not there, if the bias term or the c intercept was not there, what would have happened is it would have gone through this complete origin. So that would not be right, right? It will skip most of these data points around here. So this bias term is shifting your targeted output towards your actual or the required output. In the same way that this white color is acting as a bias to give you the color of your choice or the color of your target, rather to say. So these are the weights and the biases. This three slides, 4, 5, 6, together is making up one equation, and we call it as a predictive equation. So this is a mathematical background, like how you are going to how you can basically assume it in terms of mathematics, a little bit, a very simple one of it, when we used to perform the linear equations, right? That we have this x1 plus x2 equal to 30, and we also have this value that x1 equals to 4, x2 equal to 6. But when you add these terms, 4 plus 6, it is not equal to 30, right? Something is wrong. So 30 over here is our target variable, and x1 and x2 are our input features. But the input feature value is 4 and 6, but the target is 30, which is not equal. And if you do this, the error term is 20. 30 minus 10 is 20. That is the loss value, basically. And we need to make it, or we need to do something so that this summation term comes to 30. What we do? We use the weights and the biases. So let us say that we are introducing one weight, which is W1 as 2, W2 as 3. And putting on those weight values, we see that 26, but 26 is again not equal to 30. So we are, let's say we're introducing the bias term, which is 4. And then we see that 30 is equal to 30, right? It is coming out as 30 after the addition. That is a 100% accurate model. This is how the model is trying to fit your data as per your required output. It is trying to fit these input features as per the required output, but in a much more advanced way. Let's see what that advanced ways are. Okay, so at this point, if you see this, how will you know what are the optimized values? So when I've said that I'm using 2 parts of orange and 4 parts of blue, let's say, it is giving us our required color. But how do we know that it will be 2 parts, it will be 4 parts? Well, as humans, we do a lot of test and trial methods, right? We try to mix the proportions and we then see, observe how the colors are varying, and accordingly, we keep a record in our mind. Okay, if we mix it in this format, I'm going to end up at this result. Somewhat similar thing is done by the neural network also. It tries to get an optimized value so that the output that the model is giving out is almost equal to that of the true labels. So what that optimized value is? That optimized value is some number, and how it gets that optimization, how it gets to that optimization value. Well, there are methods to get over there. So if you think of this picture, if you take this picture, what this boy will try to do? This boy will try to hit it right at the center. If he cannot hit it right at the center, let's say this boy is hitting somewhere over here. If I mark it like the boy is hitting somewhere over here, but he wants to hit it at the center, the bullseye. So if this is the optimized point, basically, for this boy, that he wants to hit it over there, but somehow he's ending up over here. So what is the distance in between this one that he wants to hit and the one that he has actually placed the shot at? Let's say the distance is somewhat by 5 centimeters. So this 5 is going to be the loss, and this boy will try to reduce this loss, and in the process of reducing the loss he will ultimately get to this optimum point. So optimal point in term of the boy, if I say it, it will be his posture, it will be his angle, his speed. He will calculate all the physiological measurements, and then he will start hitting on that dartboard to get to this point, so that the loss is reduced. So optimization, in other word we can say, is reducing the loss. Okay. So if I go to the next slide, this is what I had explained over here. Optimization is basically reducing the loss. If you try to optimize something, that means you are trying to make the uh, you are trying to increase the accuracy of the model. So this 2 slides is actually making up again a new concept. The new concept of reducing the loss via optimization. Now as human being, you can basically look through your eyes, you can see it, and then you can perform the optimization. Okay, that if I stand in this way, the loss will be less. If I let's say have this kind of a speed or something like that, you will try to reduce the loss, you will try to be as much perfect as possible. But how the model is doing it? The model normally does it by the method called as gradient descent optimization. Now, what this gradient descent optimization is? The name is very big. The concept is actually quite, it's a bit complex. It involves certain differentiation methods. You need to know about the derivatives if you have to go through the complete structure of how we are getting it here. But that is not the target of today. I'm going to explain you this gradient descent optimization in the simplest way possible with these examples. So before that, till now, I would like to ask, are we clear up to this point or are we aligned? I would appreciate some comments maybe. Okay, great. Thanks. Okay, I hope everyone can understand. Okay, there is a lot of silence. Okay, so moving ahead, what is this gradient descent optimization? We need to reduce the loss term as much as possible, and for that we do the gradient descent optimization. What this is doing? Okay. Now, when I said that you have to align the output with your true label, you cannot change your input data. What you can change? You can change the weight and the bias. Or in simple term, I can call it as parameters. So your weights and the biases are basically your parameters. What you can do is change the parameters. So when I'm saying that gradient descent optimization, you have to change the weights and the biases in a way so that your output is uh, near to that of your true label. So what you do is, in this case, suppose I have this weight of, I'll write a little bit of mathematics. So suppose you have the weight of 10 at first. That is a random initialization because initially you are not going to know what kind of weight or what kind of bias you need, right? So model also is unaware of the fact that which weight and which bias is going to give you the maximum accurate result. So it initializes something, let's say the weight with this 10. After that, what will happen with this gradient descent optimization? It will start descending down. So as you see this picture, what happens, this cost function is basically the loss function. And as you see, with the increase of this weight, this is going down. This is an optimization algorithm. So what is happening is you are having a learning rate, and this will something like, so I'll just write down the formula at first. This is how the gradient descent formula looks like. Not this one, sorry. This is the cost function J, and this is the W. So the cost function, we call it as a J. Okay. And this is the weight which is getting updated every time. Alpha is a learning rate. Now, what this learning rate is, I'll let you know this one, but before that, what this gradient descent is doing, updating your value of W. So you are basically finding out that with the change, if I change this W a bit, how my cost is going to change, right? So if you take the example, I will give you the example at first. This is a bit complex. If you take the example of writing the codes over here, when you write a code, you are basically writing it in a flow, right? The first line of code, second line of code is depending on what you have done on the first line. Third line of code will again depend on what you have done on the previous two lines, right? You are basically following a continuous hierarchical structure, maybe the structure of the concept. So if let's say you have to change one of the concepts somewhere in your code, what do you have to do? You have to certainly go back to the upper steps in your code to see if nothing is getting affected because of your change for a single line of a code, right? Because everything is connected whenever you're inside of any, let's say, a function block. Similarly, you can consider the gradient descent in the same way. This W and J are connected. So you have to see that if you are changing this W by a bit, let's say I'm changing this W by 0.001, then how my J is going to change. That is how my cost function is going to change. That is again how my accuracy is going to change. So by that, you are basically calculating the W. And while doing it, let's say the random initial value of this W is somewhere here, which is 10 we have considered. And at that point, the cost function was this. Okay, this is quite huge. Then again, you are checking over here. That is changing the value of this W. You are changing the value of this W by, let's say, 0.001. That is increasing the weight. And then your cost function is coming somewhere at this point. And how you know that the cost function is reducing? Of course, by the same formula of this Y minus Y, to think it in a simple terms. Okay, this is how you look into it. That is the accuracy, how your accuracy is increasing. That is how much your this difference value is decreasing basically. So with the looping, with doing this procedure, you end up at some minimum value. And then again, after this point, let's say this is weight somewhere at around 12. And after at this point, if you do, let's say 12.001, you will end up somewhere over here. And again, you will see that your cost function is increasing. So you know that your minimum value for the weight is this. And at this value for this W, and for a bias also, there is the same structure. If I take another, this one for this bias term, this will be a plane, not a line in that case. So by this, you know that your W and your B has got a particular value, the minimum value, which is somewhere at this point. Okay. And with the usage of that parameter values, your cost function is reduced. This is what gradient descent is doing. And what is this learning rate? The learning rate is basically a small multiplication which is helping you in traversing the path. So if your learning rate is higher, then you might not end up at this step after this one. You might end up directly at this step and then at directly at this step. So you might skip the minimum point. That's why normally whenever you will do some coding, you will see that this learning rate is quite smaller because you don't want to skip this minimum point. This is what this gradient descent optimization is. So if you think of it as your lines of code when you do it, you can find an analogy that while writing down a code inside of a function block, you would want to maintain a flow, right? You, if you are changing some lines of code, you would want to go back and see if it is affecting other code blocks or not. If it is affecting, then you have to change that also. Same thing as gradient descent. This is how you start updating the weights. So I hope this gradient descent is clear, and this is actually a difficult concept over here. If you go on with the mathematical terms, like how this is happening inside of it, and why we do the gradient descent optimization, why it is needed, and how all these things are happening, we will see eventually. But let me know if you are clear up to this point. I hope everyone is clear, can do some maybe. But if you have any doubt, you can ask me because this is important actually to understand. Okay, there is a lot of silence. I assume you have understood. Okay, cool. So moving ahead, we will learn about the deep learning. Now, why we learned about all of these concepts. It will be clear right now why all of those concepts were required in deep learning. So as we all know what the deep learning are basically the neural network architecture. Now, what this neural network architecture is, something like this. These are the fundamental building blocks of the neural network. Is basically the neurons. Now, what are these neurons? What are this small round shaped balls over here? These are basically the these are basically the mathematical balls, you can think of it. What these balls are having, these are having the function that we just saw right now. It is having the function of this y equal to mx, let's say y equal to mx plus c. This is having this function, and there is another function which is called as activation function that I'll show you uh, in a few minutes. But this activation function is basically the sigmoid of this y. Now, what the sigmoid function is, nothing but if you say the sigmoid of this y, it is basically 1 by 1 plus e to the power minus y. What the sigmoid function does, I'll explain it to you later on. But to let you know right now what these neurons are having, these neurons are divided into two parts. So in this neuron, whenever a data is entering, first it is performing this predictive calculation part, this y equal to mx plus c, and then some activation function is getting applied on top of it. It's not necessary that the activation function has to be sigmoid only. There are other activation functions that you will get to see eventually. But this is what a neural network looks like. So there are input layers, there are hidden layers, there is output layer. This is okay. So can I? Okay. So this is what a neural network is. Now all of these inputs are connected. All of these hidden layers over here, and we call it a dense neural network. Okay. So moving ahead, if you look into the layers, this input layer is where you're receiving the inputs. It might be an image, it might be the text, it might be numbers as well. And then in the hidden layers, you have those intermediate layers where your actual calculations are taking place, where the actual work is happening. And then this is the output, which is providing the final result to you. As you can see in this one, there are multiple layers. Now you can have three hidden layers. There are three hidden layers over here. You can have multiple, as many as you want, but depending on your usage requirements. And there are four neurons per layer, as you can see, but you can have as many neurons as is required as per your business cases. Okay, that we will see later on in the project section that I have. Okay, so you might think of why we have so many hidden layers. If we go back to our coloring example, okay, where we were taking two parts of orange and four parts of blue, what was happening is that when you if you think of this color mixturing, what happens is you pick up the blue and then you pick up this orange. Then in the first mixture you are ending up it at this color, and you can think of it as hidden layer 1. Okay, this is the hidden layer 1. And then you mix the colors a bit more, you end up at this hidden layer 2. And then you do mix more of these mixtures, this is the hidden layer 3. And finally this mixture is the hidden layer 4, which is giving out the actual output that you need, right? The actual purple color, which is your requirement. So you can think of these hidden layers as this kind of color mixtures. Your numbers are getting mixed, your numbers are getting through certain kind of calculations, certain different types of computations, rather to say, this this structures, which is learning about the data. This is learning about more of your data. It is learning about the context, the word usage, and multiple other things. And then you are getting to your output. So this kind of analogy you can think of as a hidden layers, how it is mixing up. Now, I told you about this activation function. What this activation function is. To give you an example, uh, let's say you have a sister, okay, and you observe that whenever you are offering your sister some food, she is doing the work for you, okay. So basically you are bribing your sister. You observe that when you gave her lollipop, she does some work for you, and when you are not giving her lollipop, she is not doing it. So this lollipop is acting as an activation function for your sister. So if you give the lollipop, then the output is if you give the lollipop, then the output is 1. And if you don't give the lollipop, then the output is 0. Okay, so you get the work done, you don't get the work done as per your uh, food. This is what this activation function is actually. So coming back to this picture, what I can uh, show is that how this activation function is working over here. That we were talking about this equation, right? Y equal to mx plus c. But if you equate this equation, or if you know, this is basically a list of numbers, right? This is a list of numbers which is ranging from minus to plus numbers. It may be decimals, it may be anything. So this is a continuous set of numbers. What this activation function will do, it will separate it out, just like this one. It will work or it will not work. So if I say, let's say the sigmoid of this y, or this activation function of this y, it will see that if the value over here, the first value, let's say the first value is 0.4, I will check that if the 0 0.4 is less than 0.5 or not. If it is 0.5, mark it as 0, let's say. And then we have something like 0.9. Then we will check if the 0.9 is less than 0.5 or not. It is not, so mark it as 1. This is what activation function is doing, classifying your output basically. And this is what the exact thing is getting used in the logistic regression. So for the classification purpose, like if you are having an image of cat and dog, which is very famous, cat and dog images, you cannot say that you cannot represent it in the form of continuous numbers, right? You need to say either it is a cat or it is a dog. So when your output is coming out of your neural network, it is in the form of these numbers. So you need to make it go through some kind of activation function, and then the activation function is classifying it as cat or a dog on the basis of some kind of rules like this. That is, if it is less than at the threshold or if it is greater than the threshold, put it under this zero, put it under this y. This is what activation function is for the model. Now, when I say there are multiple activation functions, what are those? ReLU, sigmoid, softmax. So this ReLU and sigmoid and the softmax is normally getting used at the output level, and the sigmoid and ReLU normally gets used in the hidden layers m- mostly. So how the sigmoid looks like, the example that we had taken, sigmoid looks like this. So this is your point of threshold. This is 1 and this is near to 0. Okay, this is what the sigmoid function is looking like. ReLU and softmax are the similar to this kind of activation functions only, which is which is basically directing your input to positive, uh, to 1, otherwise 0. That is, if I show you this diagram over here, let me just click here. Okay, so this is for the ReLU. What it does is, whatever your input is, if your input is positive number, then it is going to be 1. Sorry, if your input is a positive number, then it is going to be positive, otherwise it is going to be 0. So this is what this ReLU is looking like. This is this I'm marking it in a quite bold structure, and then this is how it is shooting up. So let's say if zero point 0.4 is getting inside of it, then the ReLU will classify it as zero point 0.4. Let's say if I'm putting over here minus zero point 0.4, then the ReLU is going to classify it as complete 0. So this kind of usages are basically getting divided in a way. I mean, you are going to define it in a way as per your requirement. If it is a binary classification, you are going to use the sigmoid because you want it either as 0 or 1. But if it is not, if it is a multi-class classification, you are going to use ReLU. Okay, and the softmax in the output layer normally. Okay, so ReLU is mostly getting used in the hidden layers for classifying it in this way, so that the negative numbers are coming to 0 and the positive numbers are coming as it is. Okay, not really for the classification, that would be a wrong thing to say. For the multi-level classification, we have this softmax layer. Okay, and this is the definition of the sigmoid activation that I just explained. So what is this Z? The Z is nothing but that output. We are y cap and the Z, they are the same. This is just a naming convention of it. Okay, so I hope up to this point you have understood it. I hope no one is sleeping. Can I expect some comments? Okay, if you have any questions or if you have understood, please put on some comments. Okay, it's quite difficult to go through without knowing if you are grasping these concepts. Okay, there is no response. Okay, I'll move ahead. Fine. So you had that kind of activation functions, right? Next is coming into the loss function. So during the start only, we understood about this gradient descent problem. Now, this gradient descent, the main objective of it is to reduce the loss functions or to reduce the loss basically. Now, what this loss function is going to calculate for you the value, like what the value is, or how much is your output diverted from the true label. And for that purpose, you have this mean squared error method, cross entropy loss method. And to give you a normal example, this mean squared error method is basically this y cap minus y whole square of it, and then you're performing the mean over all the training examples you have. Let's say this in training examples. Okay, summation over all of it. So this is the mean squared error. And in this way, you are basically calculating the loss functions. These are just to name a two. There are others also for this loss calculation. And this loss function is giving you a result, a calculated value for this loss function. that value is being utilized by this gradient descent optimization technique. And then again this computation takes place. So it is basically a forward and a backward calculation going on. So when it comes to deep learning, you must have heard about this forward propagation and the backward propagation. Till now, like this y equals to mx plus c, that predictive function, then the activation function, and then this loss function calculation. Till now, we have learned about these things. This makes up the forward propagation, basically. And whenever you are calculating the gradient descent, you are calculating it with respect to that of the loss functions and with respect to the parameters, because you cannot change your input, right? So the calculation of this gradient descent to optimize the value of this W and B in a way that your loss is less is a backward propagation. Okay. So that's how this gradient is connected to loss function. So there are different kind of optimization algorithms, or there are different kind of methods to this gradient descent algorithm. There is a stochastic gradient descent, which is again updating the weights using a small batch of data, just same as the one that I have shown, that W equals to the formula that I have shown. The W equals to where it is, not here, not here, not here. Okay, let me just write it over here again. Where is it? Yeah, optimization algorithm, which is updating the weight, that is performing this W equal to W minus alpha dj by dw. This is how this yeah, this is how this update is going on for the weights, and not just the weights, rather to say the parameters, basically. So this is a stochastic gradient descent. Another is the atom. So there is another one called as momentum also, and it is combining the concept for this SGD, stochastic gradient descent, and the momentum, and then you are getting this atom. So these are all the optimization techniques. And how it is differing, it differs all in the way of its performance, all in the way of its working, which is again completely mathematical calculations. That is how it is operating on the data. Okay. So, up to now, what do we know? We know about how the input features are getting altered by the weights and the biases to produce the accurate predictions. We have seen how these activation functions are directing the output to one of the sections or one of the groups, right? Then we have seen how the loss function is being calculated to get the, I mean, it's calculating the difference in between the outcome and the true labels. And we have seen what are all the loss functions available, and there are multiple others to calculate it. Then we have seen how the gradient descent is helping in optimizing the values. So we know a lot till now. Just a few more concepts are left before we can go to the coding. And when you will go to the coding, you will say it's much more simple when you are writing it down on codes, but understanding of the concept is required so that you know at which point you should be applying which layers. Okay. So getting back, how this forward propagation, the backward propagation is working. If I give you an analogy to this, suppose you are teaching a kid to draw an apple. Now the kid has seen the apple in the markets, and the kid knows an apple looks like this. Okay, this last uh, step of this eight. So when you start drawing an apple and you're showing this to the kid, you will see that the kid is not recognizing this step number one with the step number eight. What you will do, you will then again go back, you are going back and then drawing more feature to it, that is you are then coming up to the step number 2. Then you are picking this or taking the step number 2 to the kid. Again the kid is finding difficulty in understanding the feature with what it has seen, which is the step number 8. So I'll just draw it in this way. Okay, then what you do is that you go back again and you draw this picture. Then you take this picture to the kid again, but the kid now can understand a little bit, but not completely. So you draw more feature to it. So what you are doing over here, you are doing the forward propagation. Okay, and every time you are performing this forward propagation, you are performing the loss with the target label. So when you're coming to this point, you are performing the loss with this target label. You see, okay, it is far away. Then you do some more feature addition and you do the forward propagation. And then again you check it. So you back propagate, again go to the forward propagation. And in this way, you end up with the true label with the forward and the backward propagation. Now the kid can recognize this apple. So what you have done, you have gone forward with the help of optimization algorithm, with the help of loss functions, you have minimized your loss and ended up at this label that the kid can now recognize. Okay, done. Now, since the kid has now recognized it, you are now asking the kid, okay, draw an apple for me. So the kid will draw some kind of an apple. Let's say I am that kid and I'm drawing this apple over here, something like this. Okay, very bad apple. So I'm drawing some kind of an apple like this and I'm coloring it to red and this is to green. So what you will do now? You will basically check this one, how I have performed. And when you are checking this one, what you saw? Is it near to it? It is not near to it. Let's say it is down by I have degraded it by 60 percentage. So what you are doing, basically you are evaluating here by this forward propagation, the backward propagation steps. You have trained me how to draw it, but I couldn't, I'm not that much of trained maybe yet. Now I have seen what you have done, but when you want me to do it all by myself, I'm failing at it. And how you know that? By this evaluation procedure. So this is the back propagation that I have just said, and this is the hyperparameter tuning. Hyperparameter tuning is what, it's basically whenever you are doing this alterations to your weights, to the parameters. And then when we were learning about the gradient descent, there I showed you the parameter of this alpha, which I said that this is the learning rate, and this learning rate has to be an optimum value so you do not miss out on the minimum point. And so this tunings are needed. You have to change the batch size also. These are just a few of it. There are multiple parameters that you can tune basically. So these are the batch size, that is the number of data you need to pass together. If you are having 100 and I say the batch size is 20, so that means every time 20 batches will go. And this is the number of layers, which is basically the hidden layers. And so you can basically alter several kind of hyperparameter tunings. And after that, you're performing this evaluation. So if I show you this picture where you were evaluating how I performed in drawing the apple, and basically I'm letting you know here, I'm giving you an analogy to that example basically where you were evaluating how I am performing. Okay. So you gave me, let's say, this pen, paper, and the colors, and you asked me to do it again. So this one, this is an analogy to the test set, which I haven't seen completely. Okay. So this is a test set, and then you are asking me to draw the apple, and then you want to evaluate how much I am accurate or how much I am closer to what you have done. So there are these three important things that you should know, and these are all being applied into the LLM fine tunings and into every deep learning model that you will see. So one is this loss function, this optimization function, and this evaluation. Okay. So this loss and optimization is basically done by you while drawing this apple to see how much I can recognize it. And this evaluation is done by you at the end when I have given you the result. Okay. And these three parameters are needed. And I hope this concept of three parameters are clear. Not the parameters, but the functions rather. So I hope this concept of these three functions are clear to you. And just like the optimization algorithm, the loss functions, and we also have this evaluation metrics, and many of it you know about it. This is accuracy, precision, recall, F1 score, AUC, ROC scores. These are the same evaluation metrics that we do in the machine learning as well. Okay. So are we clear till this point? I will move to the projects now. Am I audible? There is no response I can see. Okay, ROC AUC is a curve, and for the calculation of it, we do have a function in the scikit-learn where you can calculate this ROC AUC, and it is normally used for the classification purposes. So it's quite different to, what we will be doing right now. Okay, I will let you know about this AUC ROC or what the concept of it. Let's go back to this our project right now, and at the end I will let you know the concept. Okay. I don't miss out. I don't want to miss out on the flow, so I'll let you know this ROC at the end of this today's webinar. Okay. Okay. Fine. So moving ahead, this is a little bit about the CNN architecture that I have showed over here. Now, the architecture that I was showing previously, I mean the layers. I haven't shown you any architecture yet, but I have shown you the layers. What those layers were? The layers where of this loss optimization evaluation is coming under one layer, which is the compilation layer. Then there are many other internal layers or the hidden layers that we have, that we were explaining as, that is a model layer, sequential layers. We will see that in the code right now. But before that, before jumping onto the code, I just want to give you a very brief introduction to this CNN, because CNN architecture is widely used in the image classification problems and in the textual data also, but normally we do not prefer to use the textual data in the CNN because we have a different architecture for that, and I'm going to use that only for our today's project. I'm not using the CNN architecture for our today's project, but this is how essentially it is looking like. Now, the architecture that you see at the end over here is something we know till now. Okay, we know this portion till now with all our input features, with all these activation layers, with all the compilations, all the densely connected hidden layers. We know this much. What are these things? Why these things are needed? You see, these deep learning architectures or these deep learning neural network layers are also prone to overfit. Okay, so we don't want to overfit the model. We don't want to bombard our models with excessive information than required. That's why this concepts came up. This convolution concept, this max pooling concept. This convolution concept is actually very interesting. What happens is that let me draw it over here. If you have a picture like this, and the picture is made out of pixels, right? This kind of pixels are there, and let's say it is a 64 by 64 pixel picture, and every pixel over here, this every block is your data, this everything. So you cannot skip out on everything. What you can do, you can extract information out of it. Convolution does the same. So if I give you an example of like this thing that you have done in your school or college, maybe the linear transformations, like if you have a square box like this, okay, and if you change it a bit, let's say this is a square box, this is at 1, this is at 3, in along this x-axis, this is 1 and this is 3 2. Now if you change, let's say 1, if you add 1 to it, and with 3 you are adding 1, so where you will end up 2, and then end up at 4. So is your structure changing? Are you losing any information? No, you are just transforming the data. Similarly, in this case, what we perform is a dot product. So there is a small thing which is called as kernel, a 4 by 3 by 3 or 5 by 5 kernel. Mostly we take it. That is, let me take a 3 by 3 kernel, which is a 3 by 3 matrix basically. And what happens is that this kernel is having data like this 0, 1, 0, 1, minus 1, 0, 0. There are different kind of kernels like this. And you swipe these kernels on top of these blocks. So if I draw a simple picture like this over here, what you do is, this is your input image, this is the kernel, okay, and you do or perform the dot product with your pixel values and the kernel, and that is resulting to a single block, that is a smaller block. Now you are shifting your kernel to the next position, and then again you're performing the result, and then you're shifting to this one. So your 3 by 3 kernel, that is your uh, 9 boxes, is basically amounting to a single box. So what you are doing, you are basically reducing the pixels. You are reducing redundancy, maybe you can say it in that way. So in this picture, if you see this 28 by 28 pixels, you are performing the convolutions, and here they are using this kernel of size 3 by 3, the one that we have seen. And then it is convoluting the results into 30 to 28 by 28 matrix formation. Now, what this 32 represents, what this 28 by 28 represents, these are all 32 is basically the number of records. over here is representing 32 images. Now then you're performing this max pooling. Max pooling is basically picking up the maximum value out of the data. So if your kernel size is 2 by 2, it will put on a 2 by 2 matrix on top of your convoluted image, and it will pick up the maximum data. So let's say if I have this 10, 2, 3, 4 like this, max pooling will pick up this 10 and then it will project it over there. Okay. So these are all the mathematical informations which are going behind it. And if I have to explain it to you, like what this 32 28 by 28 is doing, and how we are getting up to this 64 here, this will be wide broad, but let's not go over there right now. Let's stick to our project. But this is what the convolution is. So this 32 by 32, it is basically dividing it this image into 32 layers. I can say there are 32 images out of this single image. So when I say this 32 images, it is not 32 different images, it is 32 out of this image. It is getting convolved. Okay. And then you're performing this max pooling, then again convolution, then again max pooling. So when I showed you that picture of color mixtures, there were multiple layers in which you mixed the colors. So this you can think of it that way. You're performing multiple calculations on your data, and then you're ending up at your numbers. Okay, so I'll show you this example as well. Okay, so first I'm going to show you a project on the chatbot, and this is a very simple chatbot. And remember this one because we are going to build our own chatbot using LLMs as well. So this is the most simplest one, but the LLM chatbot will be quite difficult in terms of concept, not in terms of code, because the codes are quite simple with the huge APIs that we have right now. So let's go back to the project over here. Now I have explained everything I have written in this. I've described all of the steps that I have performed over here so that you can go through later on. Of course, no one can remember it at one go. So please to read all of these informations. Okay. I am importing multiple libraries over here. This library, everyone knows about it. Then I have imported this TensorFlow library. This TensorFlow library is basically for performing the deep learning operations. Just like this NumPy for the mathematical computations, TensorFlow is for the deep learning operations. And then we're using Keras. Keras is again a sequential model architecture. What do I mean by that? So everyone here knows about the Python OOPS concept, right? Whenever you are building a class, you are defining multiple functions in that class. What that functions are performing, that functions are basically depending on that class, right? So when you are creating an object of that class, you can basically utilize all of the methods, rather not the functions. The accurate term would be methods. So you can basically utilize all the methods belonging to that class. Similarly, this keras is based upon the TensorFlow, and it has multiple uh, subclasses like the sequential and the dense embedding, this global average pooling 1D, that are useful for your operation. Now you already know about all of these things. We have already explained everything of it in the PPT. These are just the names. So what the sequential is, the sequential is going to build up the layers for you. So you can think of sequential as your container or a box, okay? And in that box, you are going to put on your objects or put on your layers. So you are importing the sequential class from the Keras models, and then you're importing this dense, embedding, and the global average pooling 1D. So what is this dense? Dense is a class for building dense network. So you need this dense. Why so? For this purpose, if I go back to this PPT again and I show you this neural network structure here, this is the dense. So every neuron is connected to this. Every neuron, this is what this dense class is going to do for you. And the sequential is basically this complete block it is going to build. That is a sequential architecture you will be building. Okay. And this embedding, as the name suggests, it is going to perform embedding on your integer data. So at first, whenever you are having the words in the last class also, I we were going through this, that machine learning codes or the deep learning codes or your computer cannot understand English. You need to tokenize it. That is, you need to change it into numbers. I have given examples for this tokenization is, but let me tell you, if I have this kind of a structure, let's say, I'll just use this one. Let's say this chatbot. So this chatbot machine cannot understand chatbot. But if I tokenize it, if I say that this chatbot is equivalent to 42, machine will understand it as 42. But still, this is not a very proper or appropriate information for the machine to understand. So what deep learning does? Deep learning embeds it. Deep learning converts it into this kind of a vector form. Okay, this embedding layer is doing that thing. This embedding layer is basically picking up your integer encoded word, this integer encoded word of 42, and converting it into a dense vector, that is in a point representation, 0.1, 0.5, 0.9, or 3.4. There are multiple kind of decimal format representations that it is going to do it for you. Okay, and embedding is also required along with the paired sequences. Why so? Because the model expects you to give it a constant input. That means one input you are giving it in this, one input is having the length of this, let's say 10, another input is having the length of this 12. Model cannot work properly with that and it might throw error as well. So you need to pad this one. Since this is 10 and this is 12, what is your maximum length? 12. So you are going to perform padding. How you perform padding? By introducing zeros at the end or zeros at the front, or you might also introduce some other numbers, but normally people does introduce zeros. So if I have numbers like this, it is 5, 4, 3, 1, another I have this just 1, what I'm going to do, I'll apply this padding over here, that is 100. This is called the post padding, so that this two matches, the length matches. Okay, and what this global average pooling 1D is doing? This is performing an operation just like your convolutional neural networks. Over there, when we were showing this convolutional layer, it is performing operation on top of your pixels, and then the max pooling is picking up the operation, picking up the maximum out of this kernel method. Similarly, this global average pooling 1D is also performing some calculation. What it does, it basically takes the average of all the element uh, in your input array. Basically, you can call it as a this array, or normally they call it as a tensor, but this is basically, you can think of it as an array. If the tensor concept is quite difficult for you right now, you can think of it as an array. Okay, so there are multiple numbers in that array. This global average pooling 1D is going to average it out. Okay, and this is the label encoder. You know what it does: tokenization, pad sequences. Fine. In case you were not in the last class, this label encoder is basically encoding all your textual data. Again, for the same reason, because computer cannot handle words. So I have this one JSON file over here named as intent JSON that I'm using. How this JSON file is looking like? Let's see. I have one tag, one key called as intents, and inside of it I have this key called as tag, pattern, and the responses. So this tag is will be used in our chatbot. This is the pattern which the chatbot is basically going to look for in the input result, and these are the responses that our chatbot is going to give out. So you can add as many tag, patterns, and responses as you like to it, and build your own very basic chatbot with neural networks. Okay, so I'm picking up this four list: training sentences, training labels, labels, and responses. What this would be? So in the intents, in the JSON file, you have gone through those intents. In my first intent, so it was a very long list. Basically, this is one of the intents, and there were many other intents in that data. I truncated the data to just a single intent. Okay, so that's why you see it in this format. For the first intent, what we are going through? We are going through the pattern. Let's see what the pattern is representing. The pattern is representing like this: have a complaint, I want to raise a complaint, there is a complaint about a service. So I'm putting it all in the training sentences. This training sentences will be the input feature for our model, all these patterns. And what will be the labels corresponding to those patterns? The tag, complaint. So these are my training sentences, and this is my label to those training sentences that the model is going to understand. And this is the responses. Responses means this one. So what are the responses the model should be giving out whenever the input is like this and the tag is like this? Okay, so basically you can think of both of it, like whenever this input is like this, what the model should be giving the output as, and these tags are basically used as a label for making the model understand. So where we are using the tag, we will see in this model architecture. Okay, but before that, let's see. Whenever, where we did this initializations and we did the appending in this list, and here you see all the list. These are all the responses that you can see. So whenever the training sentence over here is basically this ones, and the training labels are over here this ones, and these are the labels, the responses. So if you look here in this training labels, so whenever it is a greeting, you are supposed to say hello, hi there. Okay. Okay, sorry, this is the label. Hello, hi there. Whenever there is a goodbye as a label, you are supposed to say this. Whenever there is a thanks, you are supposed to say this. Basically, we are placing this, or we are getting ready with our data set over here. Now, the number of classes, or we can say the number of unique intentions that we are going to let the model know, that is the number of unique labels that we are going to let the model know, which are basically the tags here, are 8. And these are the labels that you see, and these are all the responses corresponding to those tags. Okay, fine. Next, what we are doing is performing the label code encoder. So I have given an example over here. As you see, this is a greeting. Whenever this is just an example. I'm not sure if the label encoding has done the same thing or not. But this is an example, like whenever the label is greeting, the model will look into it as 0. Whenever it is goodbye, the model will look into it as 1. This is the label encoder, where you are passing the training labels to get the encoded format out of it. Right? Okay, so now our main part starts. We need to perform the tokenization at first. Remember these terms over here. This vocabulary size as 1000, embedding dimension as 16, max length 20, OOV token is basically out of vocabulary token as OOV. What this vocab size represents? The vocab size is representing the maximum size of your vocabulary, or the maximum size of the words that the model can take into consideration. Okay. So this vocab size we have placed it at 1000 means the model will consider the top 1000 words and it will ignore the other or the less frequently appearing words. Next, we have specified this embedding dimension as 16. So what we said, what the embedding is, if you go back here, the embedding is basically this 42 number, this integer number is getting transformed or converted into the vector formation. So that is what embedding length is. So if it is going to get converted into a vector, what should be the size of it? The size maximum should be 16. So if you have 42, change it to a vector of dimension 16 and not more, not less. Okay, so it might be less at some point, that's where we are performing the padding, but yes, this is the maximum size. And at some point, when you will be working with the larger sentences, it might happen that your vocabulary is increasing a lot, the vector size is increasing a lot, but your maximum uh, vector size that you can permit is, let's say, like 20. So you need to truncate it in that case. So why am I saying this? Because when we will go to LLMs, these concepts will be very much important, because different LLMs has got different kind of different what to say, this tokenization length formats. For example, this T5 has got this 512, and this GPT is normally 1024 tokens that it can accept. So this all depends on this same concept only, this dimension concept. Okay, and this max length equal to 20, what it is doing is setting the maximum length of the sequence. So if you have any kind of a sentence which has got larger number of words beyond 20, it will get truncated. If it is a less, it will get padded. Okay, now how all of these things are happening? These things are happening in this lines of code. Just in this 5 lines of code, you are performing the tokenization and you're performing the padding as well to all of the sentences. And over here, when you see this truncating equal to post, What it means, if your words are less than what is required by the model, or less than the maximum size rather said, then you are going to add zeros at the end. But if it is greater than the maximum size that you can accept or you have specified, then you need to truncate it from the end. Okay, I hope this is understandable. And what this OOV token is doing, okay, this is the out of vocabulary tokenization. Now, your dictionary or this tokenizer that you are using, this tokenizer might not have certain words in its dictionary. Like if I give my name over here, my name might not be in the dictionary, it might not recognize it. In that case, I need to place some kind of a token so that the model understands, okay, this is not in the dictionary, this is some other new word. Okay, we just specify it, or we just make it stand out of the rest of the vocabulary that it has. Fine. So this is a tokenizer, and this is how the parrot sequence shape is coming up right now, 3320, and these are all the training label shapes. So training label is ending up at 33, and over here you see that the maximum length is 20 that you had already specified over there for all of the words. Okay, fine. So moving ahead with the model building. First, you're initializing the model with the sequential. So remember when I said that sequential is basically acting as a box where you are going to place all your objects. And in this case, you are going to place all your layers. So this is a sequential, and into this, we are going to place or add the layers. What those layers would be? First is the embedding layer. So embedding layer is first going to convert all your integer numbers into the vectors, and the vocabulary size should be 1000 maximum, and the dimension should be 16. That means that whenever your input is going to get inside of it, I mean, if I show it over here, taking the example of this 42, where is it? Okay, taking the example of this 42, when I specified that this embedding should be the vocab size and the max length of this 16, this is going to get converted into a vector like this, wherever the dimension is as per specified over here, this vocabulary size. So this is the vocab size of this 1000, and this is the 16. So there will be 1000 rows with 16 number of columns. So if I consider this an array, there will be 16 columns and there will be 1000 rows to which this 42 is going to get embedded. This is the embedding layer forming a dense vector. Okay. Now, in order to understand it more appropriately, you might have to go through first, if I say it from starting from the linear equations to how these vectors are forming up, how these kind of representations might show up over here. Okay. So essentially, this is like this. Now, next is the global average pooling 1D. What it is doing, it is going to find the average of all the numbers in coming out of the previous layers, but um, keeping up the dimension basically. So if you remember that max pooling, what it was doing is picking up the maximum from that kernel. In this global average pooling only, we are not having anything as kernel, but it performs just average. So on top of what? On top of this, whenever you are writing the model in this format, first this line will be executing. So this is one layer, and the output of this layer will go to the next layer. So this is going to perform the average on the output of the previous layer. It will use the output that is this one, which is in the form of a sequence, and it will compute the average on the numbers so that the dimensions are reduced, and that will be much more efficient, that will be much more accurate if you're reducing the dimensions to get only the important information. Okay, so this is our second layer. Now the output of the second layer is going to the third layer. This third layer here, as you see, 16 is written. What is the 16? 16 is the number of neurons. There in the picture, we observed these neurons over here. There are multiple neurons, as you see. In this case, we have used 16 neurons and the activation function as a ReLU. So what this activation is again doing, if it is a negative, it will be 0, the sequence, and if it is a positive, it is going to be in that positive number only. This is the first dense layer, and this is the second dense layer again with 16 neurons, and then this is the third dense layer, and in this case, this will be the output layer for us. Why so? Because we are passing the number of classes. Now what was the number of classes we had? We had 8 number of classes, if you remember. Just we had seen it above. So we are passing this 8 number of classes and a softmax. So the softmax is basically going to pick up the it is going to basically pick up this output from this line, this fourth layer, and this fourth layer is giving you probabilities. Okay, and out of that probabilities, this activation function of this softmax is going to pick up the class with the highest probability. And an example of it is, I have shown it in this title generation project, which I will show in few minutes. Okay, so in this model, if you see, there are 5 layers that we have added. Now the model has to do or perform some kind of compilation that we have already seen. The model has to perform the loss, and the loss function over here is the sparse categorical cross entropy. Why it's a sparse? Because there will be a lot of zeros over here. If you perform the encoding of it, and we have passed the vocab size of 1000, but the maximum length of our input data might be 16 or 14 or maybe less than that even. So there will be a lot of zeros. That's why we're using this sparse categorical cross entropy. If you want to know the broader detail, of course, you can go through this documentation, like when to use what laws. And there are not many laws and optimizer functions available, so it's quite easy to remember. But yes, we do get confused, right? So you can go to the documentation for referring to these parts. Okay, so getting back, this is the model compilation step where you are using this loss function, and the optimizer is the atom, which is basically the gradient descent calculations, and this is the metrics or the evaluation that we're performing is with the accuracy metric. Okay, and if you want to know your model architecture, this is how you can get a view of it. Model.summary. So as you see, there are 5 layers. First is this embedding layer, then the global average pooling, dense 1, dense 2. Over here, you see everything is written as 0. Why? Because we haven't trained the model yet. This is just the model building. So all the concepts that I was explaining in the presentation is basically shrinking down to this few lines of code. This 6 lines of code, or this 7 lines of code if I consider this one as well. So just with the 7 lines of code, all of this concept is shrinking down, right? So understanding the concept, even over here, what I have shown you is just the top view of it. If you try to understand the mathematical ones, which you should, then it's very complex. But all that complexity is getting reduced to this 7 lines of code thanks to all this beautiful APIs, right? So this architecture is built and your architecture is looking perfect. After that, what you have to do is fit the model. That is, now your architecture needs to see the data for which you have built that architecture. So this is your padded sequences or the input features, or your processed input features rather. And then this is the training labels or the output. And then you are performing epochs. What are the epochs? Epochs are basically, you can think of it as loops. So you are running 500 epochs, or you are running this model 500 times with the data, with these padded sequences, with these training labels. You are running it 500 times, and every time it is running, it will give you this kind of a thing: accuracy and the loss, accuracy score and the loss. So if you go up till at the start point, you will see the accuracy values are increasing, okay, and the loss values will be decreasing. So till you go at the end, and here you see somewhere at this point the accuracy was high, this 496, and then again the accuracy started decreasing. So somewhere my model is facing an issue in finding out the minimum point. So probably I should have stopped at this 496 epoch when my accuracy is high. So I can think of it as, at this point my model has got the weights and the biases which are the most accurate ones for this model. in order to reduce the loss. Okay. Now, if you do the model summary, you will see these parameters. So, before the model training, this architecture is not having anything. But just after the model training, you can see that this architecture is having all these parameters. Do you have any question? I can see someone maybe unmuted. Okay, so I guess there is no question, so I can move ahead. Okay, so this is the summary. Now you see this summary. In the first layer, there is 16,000 parameters. In this layer, there is 0. In this layer, there is 272, 272, 136 total parameters, non-trainable optimizers. Oh my God, so many things. What are all these things? I have explained it all over here. What are all of these things? Yeah, to give you a brief, what is this embedding layer? If you think this is the output of this embedding layer, that is when the embedding layer is taking the input, what kind of output this embedding layer is passing to this layer? This output, this is the shape of the output, and this parameters is 16,000. What is this? Since I explained that there is a vocabulary size of 1,000, right, and you have specified the maximum dimension to be 16, so 1,000 into 16 is 16,000. That I have explained it over here completely, what these are all representing. So there are 16,000 parameters for it. In the second layer, it is only the average is going on. So no parameters are there really. It is not, the model is not having any parameters to learn from. It's just the average to reduce it. Okay. So from here, you see that this output shape of this 20 and this 16, none is basically the batch size. Uh, and we are not passing it in the batch format. The batch format I will show you in the title generator. So this is not, and this is 20 and 16, and you can see that this global average pooling is reducing the dimension. 20 is nowhere to be seen. Why? Because it has already performed the average and the dimension is reduced. So this is quite easy to understand it from here. And then this is getting passed through this first dense layer. Parameter is 272. Why so? Because the number of parameters that are getting calculated in the dense is always the input dimension plus 1 in the number of units. So what is the number of unit? 16. The input dimension is also 16. So there is 272. And if you sum up in this way, all of these parameters, you see the total parameters will be, the trainable parameters will be 16,680. But your total parameter is showing us 50,000. Why so? Because when you are performing the gradient descent optimization, that procedure is itself taking up some of the memories. That's why the parameters will also increase in that case, because you're updating the W and the B multiple times. And over here, there is not only a single W or a single B, there are 16,000 parameters. So these 16,000 parameters, and then this 272, 272, 136, all over is 16,680. This many parameters, the gradient descent is trying to optimize. So in the procedure, it stands up to 33,362 parameters. So these are the optimization parameters. And together with this and the trainable parameter, you end up with the total parameter of 50,042, right? Fine. So over here, when you see this total parameter is this and trainable parameter is this, when you will start with the LLMs, you will see it will go up to millions. That's a huge models. So the understanding capability is very huge for those, right? And it's done. Your model is ready. You can save your model like this. So I have introduced this part, some extra. You can directly use it, but I have showed you, I wanted to show you how you can save the model and then use the saved model. Okay. In the next webinar, I will show you how you can use the Streamlit to deploy it. Okay. So your model building is done. Just in few steps, you are ready. Deep learning is quite easy when it comes to coding, but not easy when it comes to understanding. So you are using your model right now. I'm doing it from the beginning. I'm again picking up my file the same way, and now I'm loading my model. So keras.model.load model is used to load the model. Then the tokenizers also you have to save. So if you have gone through a little bit of LLM somewhere, you must have seen that when you are downloading the LLMs, it will download the model for you as well as a tokenizer for you, because every model has its own set of tokenizer or its own set of representation to the words or the sentences rather. So You're picking up the model, you're using the tokenizer, the learned tokenizer, and then you're using the encoder, also the learned ones, and then you are iterating. You have started one iteration. What this iteration would be? The iteration is like this. So if I go to this example here, if you run this and call this function as chat, it will ask for your input, and then you're passing hello, and the chatbot is saying you hi. You say that I have a problem, then it will let you ask you, please let me assist you or something like that. So over there, if you say, let's say problem fixed, when I prompted it that problem fixed, the chatbot said hi there. That's strange, right? Because my chatbot is unaware of what to do when there is something called as problem fixed. So it is just giving me some random response out of its learned ones. Now, when I said it bye, it is telling me anytime, and then I have to press quit in order to end this loop. That's how this while loop is built. So how this is happening? The same thing. You are passing, this is my textual data, right? So this textual data is my input over here that I'm tokenizing. I'm performing the truncation as well, in case the user is giving some input which is greater than what my model can take, and then I'm padding the sequences, and then I'm using the prediction, and this is the result. And this prediction, if you remember, that is a softmax we used, right? And the softmax is giving you the probability scores, and from there I'm using this np.argmax, that is, it is going to return you the argument of the maximum number, and then we are performing this inverse transform to get back the word, basically to get back the tag. And then this is what you can see, that if the tag is matching with the tag that it has picked up out of your prediction, it is going to return the corresponding response to it. So I'm not having any kind of a response to this one, that's why it is bizarre. But I'm having a response with respect to hello, I'm having a response with respect to have a problem, so that's how it is giving me. So this is a very basic deep learning model here you have, but it is very important in terms of understanding the concept, and it is using the dense layers. So these layers you see over here are the dense layers. This is not convolutional neural network yet. Convolutional neural network is something different. But before that, let's move to the last project, that is the text generation. And this is a brief introduction, and I have given a brief introduction for the LSTM layer. Just like the way we used the embedding layer, the dense layer, there is another concept of this LSTM layer, which is a type of recurrent neural network, that is another architecture. And this LSTM is an extension of this RNN architecture. Now, if you have to understand this, you need to understand the mathematics behind it. So if you see here, this one's I hope it's visible. If you see here, this ones, these are the sigmoid functions being used. This is a tanh function being used. So you see there are so many mathematics involved if you have to understand the architecture, but if you have to put it on code, it's just one line, just like the way you have done this. In order to understand this average pooling, embedding, dense layers, you need to go through these activation functions, the gradient descents, but while doing it, it's just one line of code with the names specified for your desired loss function to use, for your desired uh, activation functions to use, right? Similarly, we can make use of this LSTM that I'm going to do now. So same things that I have imported, but I have extra of LSTM and this dropout and this early stopping. LSTM is the same layer that I have showed you in this presentation. This is the complete architecture, the broad architecture of it, basically the broad architecture of LSTM. And when you are using this LSTM from this keras.layers, it is going to do the complete thing for you that you have seen in that picture. You do not have to build anything from scratch. Like this is an LSTM API. Dropout, it is a technique which is helping in reducing the overfitting. So it is going to ignore certain kind of neurons or certain neurons. Whenever you are building it, there will be multiple neurons while working with these LSTMs, because when you are working with the words, when you are working with sentences, there are multiple words. I mean, your even a single word is divided into multiple tokens. For example, if I say the word the is a single token only. But if I say, let's say this one, this converting, this will get, this is a single word for us. But when we will tokenize it, it will get divided into multiple words, maybe convert and then ing. So one is convert and the second one is ing. One word getting into two tokens, rather to say. That's why this dropout is sometimes important in order to avoid the overfitting. And what this early stopping will do, remember when in the chatbot I was showing you that in this 496 or something, in this 496, the accuracy was higher and then it started reducing. But then also we went on with our model training. So what this early stopping is going to do? Early stopping will stop the model basically. It is for the early stopping of the model. Whenever the model will see that your accuracy is decreasing, it will stop right there. Okay. So here I'm using few data sets that I have taken from Kaggle, and this is the data set. Over there, the data sets were in a separated format. That's why I have to pick it up separately and then concatenated it. So this is a bit of a pre-processing task that I have done. It's quite simple. It's quite intuitive. Nothing really different to explain rather than this part that this is a category extractor. So you have this two data set. One is this CSV data and one is this category data. So I have just picked up these categories over here. Like you see that this is the ID of this 30, and over here I have this category ID somewhere. Okay, so if I take a same example of this, let's say I have this 24. Yeah. So in this category ID, I have this 24. I want to convert it into a title because that's what I want to generate, right? So corresponding to this 24, what kind of category do I have? I have this YouTube video category, and it is going to replace the title for me. Okay, that this function over here, category extractor. Okay, so after extracting the category, what am I getting? This one's this category title, this column that I'm fetching from my JSON file and ending up at this point. This is the, these are the tags over here. This is the category ID. Using this category ID, I extracted this category title. Now, if you look into it, there will be multiple category title, and the reason I picked this one up because I used this entertainment for the text generation purpose. You can use other category title with this code and try it out. Maybe people and blogs, maybe comedy, and there is others like this sci-fi also that you can use of. So I have picked up entertainment from here and I have selected 4000. Okay, this entertainment data set, when I filtered on it, there were multiple records. Can we use CPU? Oh, no, you cannot use CPU when you are working with deep learning models. You can use if it is a very small model, just like the one I did in the chatbot. It's a smaller one. I used CPU in the collab. But if your model is a huge one, CPU will crash, your RAM will die. Okay, so it's better to use a GPU. So you can make use of this collab notebook, and this is the reason that was I was actually going to say that uh, I'm using this one GPU T4 over here. So going to this Google Colab, you can click on this change runtime and you will see this T4 GPU, CPU, and this option. So click on this T4 GPU to use the GPU. So I have it already selected, fine, and then I used this one. But since this is a free version, the GPU power is limited. So it's better if you have a GPU in your own system. Otherwise, it will be a bit limited, yes. So since I'm using it on Google Colab, I have a limited GPU resource, and that's why I'm shrinking the, or I'm rather to say, I'm picking up just 4000 records. There were many, but I picked up 4000 records for the purpose of this demonstration. Okay, and so this is how the titles are looking like, this entertainment titles. Okay, then I'm doing some kind of a text cleaning. Okay, but I haven't removed the um, stopwatch from here. That's the usage, or let's say that's the beauty of these models, these deep learning models, that you can keep this ones. Why? Because at many times this grammar does have certain meaning. This grammar can change the context of your sentence, right? So keeping this grammar is important, and that's why it is not generally, the grammars are not generally removed when it comes to the deep learning neural networks. Okay, so if you see this one, I have named it as corpus. If you see this one, you can see there are 4000 records, or I can say that 4000 individual cleaned titles. Okay. Then we are performing the tokenization the same way as we have done for the chatbot, but over here I have done a little bit extra. What? That is n-gram calculation. So, n-gram, what is that? If you have a single word, that is just a word. I mean, I'll just show you here. Uh, okay, if I pick up this one, LSTM is a type of recurrent neural network. If I pick up this sentence only, okay, from here to here, this is a complete sentence. If I say it's a 2 gram, if I want to pick it up as 2 gram, what will happen? It will be like LSTM, then is a, then a type, that is 2 words. Okay, this is a 2 gram. A type, then type of, and it will go on like that. If I use a 3 gram, then how it will be? LSTM is a, then is a type, then a type of, in this way it will go. So with the increase in the grams, basically you are picking up extra words. Okay, and I have the output ready for it. So after this, what do you see? That there are total words of 7997. Wait, there are so many. How it came up to so many? Because we are using the n-grams also, right? So how it is looking like after the n-grams? Let's check this one out. In the corpus, what we said, those are the clean sentences. So if you look at the first sentence, this is what the first sentence is saying. The Trump presidency last week tonight with John Oliver HBO, right? So there are 10 words. And when I passed it through the tokenization via n-gram method, it has given me this format. So first is the 2 gram, then is the 3 gram, then is the 4 gram, and in this way it is increasing up to 10, which is the maximum number of words that this sentence is having. Okay, so the length of the corpus is 4000, but with n-gram method it is getting converted to this. Why so? Because of this reason. In order to generate the text, in order to understand the context, you need to divide it into this format so that the model can understand what is likely to come after what word. Okay, so if you now look into this one, this tokenizer.word index, if you write this tokenizer.word index, normally you will see that there are many key value pairs you are getting. The values are the numbers corresponding to the key values. So what I want to check over here is that the word index for the, and you see two. So in this sentence, you see the, and over here so many two. So this two is representing the definitely. Next, if you want to check out the word index for this John word, and you see 113. Yes, this John is the last third word, so it is coming in this n-gram, this n-gram, this n-gram as per this context. Okay, so this tokenization is happening in this way. These are the individual numbers, right? These are not vectors, but our model expects to see it in the vectorized format. And rather, to tell you accurately, the model expects a tensor, and a tensor is always a 2D, not a 2D, but always an even shaped matrix. You can think of it. Okay, so we need to convert it into vectors. Before that, we are performing the padding. The concept is same as that one. I have elaborated every line. So the padding is introduced in all of the sentences. But over here, there is one thing that you are separating out the predictor and the label. Predictor are all the words in the input sentence except for the last word. The last word is the label. So what your text generation basically does, when you are typing a message on your phone, you will see that just on typing one word, the that Google keyboard is giving you a recommendation that you can use this word next. Okay, that is the word recommendation. That is, if you are having a word, what should be the next word? In order to make the model understand that, you must pick up the words coming before your word to predict, that is coming before the last word. That's why we did so many n-grams over there, so that when we are passing all of this to the model will understand in this way. So getting back here, the model will understand that, okay, so whenever there is 2 and 69, the output should be this. Whenever there is 269 3389 3381, the output should be this. Okay, so that is how we are separating out our input features and the labels. Fine. Great. So after that, what we are performing over here is this one hot encoding. So this one hot encoding is similar to that of the vectorization performance kind of, but still we are going to use the embedding layer. Okay, one hot encoding, we explained it in the last class, and I guess it's a normal concept that we know basically. Writing out one for the places wherever the number is present and zero for wherever the number is not present. Okay, and after that, what we are ending up to? We are ending up with the label of this much, and these are the predictors of this much. So the predictors are, as you can see, there are 28,813 records, and each of it is having 21 columns. Okay, that is the dimension of it. Great. Now, the question that can we use CPU? You cannot, you have to make sure that you have a GPU, and this is how you can make sure if your device is having a GPU and your code is GPU enabled. So, using this code of this TensorFlow, I can see I have a GPU. What I'm doing is setting up over here that my physical devices set my memory growth to GPU. That is, my model will run on GPU now. Fine, great. So this create model function is doing the exact same thing as we have seen in this chatbot one, but with different sort of layers. That is LSTM, and dropout is extra over here. So you have the same thing, the sequential being built up. You have the same embedding layers where you are letting it know what should be your output dimension and what is the vocabulary that is the input dimension, and it should be the maximum. And you're setting up a maximum length basically. You want to truncate if it is, sorry, much more greater, and then you're adding up the second layer, which is the LSTM layer. Now here you see the LSTM layer is 100 layers, which is quite a lot, right? And then you're adding the dropout layer, that is 10 percentage of the neurons will be dropped out with every training because we don't want to overfit it. And these are the parameters that you can change. So when in the presentation I explained about the hyperparameter tuning, it is basically the tuning of these numbers. If you see that your output is not as per your required one, you can change this dropout value, maybe change the dropout to 0.05 to 5 percentage basically, and change these LSTM layers to make it even more or less, whichever is coming out to be accurate one. And then we're adding the dense layer. So dense layer over here is the last dense layer that we have used over here. In this case, if I go back, this is the dense layer where I, not this one, this is the dense layer where I was using the ReLU activation function. Here I have used the activation function as a softmax. And then, okay, sorry, no, this is the last one that I have used equivalent to it. That is the output layer. So output layer is using the softmax activation. This is giving out the probability score. So I have shown you in the output how the probability scores are looking like. We will get to that point. And this is again the compilation. Here we are using categorical cross entropy, Adam optimizer, and again the accuracy metrics for the evaluation purpose. Then we are creating the model and then fitting the model with our input features, which are the predictors, and then the labels. And I'm using 30 epochs over here. Now in the hyperparameter tuning, you can change your epoch numbers too and the batch sizes too. So when I say 32 batches, that means this model is going, the data is first being divided into 32 batches, and the model is going to run 30 times on top of this data, which is divided into 32 batches. And this verbose is basically going to show you this one, this output. So over here, you see the accuracy of our model is not up to the point, right? So I ran it again. I ran it again for the 20 epochs. Why I haven't ran it together? Because my model was going out of memory. So after performing this line, my model is now knowledgeable about the data, a little bit knowledgeable. So with that learned model, I'm again fitting it. Now you see the accuracy is increasing. Now again I ran the model for 10 times, and you see the accuracy has increased to 75 percentage, and the loss is more or less the same. So the loss is not reducing, it is more or less the same. This is an indication that you might want to change your batch size and the LSTM numbers and the dropout value. Okay, and now your model is trained. You can use that model to generate the text for you. So I have used this printing statements at every possible points. You can remove it, but this printing statements I have used to show you how this output is looking like. This is how the output is basically. So what you passed over here, let's say this text of this Shiva, and you want to see what the output is, and you want the output to be of 7 words long. not more than that. You're passing your trained model, and this is the maximum sequence length, which is again the length of your maximum sentence. So you can pass it or you may not pass it also. This is an optional thing. But you need to pass this 7 and you need to pass the model 7 because you want it to be 7. And you can also keep it a constant one. That is, whatever the user might give, the sentence output will not be more than that number. Okay, you can keep it static also. So let's see what is happening. When I passed over here Shiva, the word is getting tokenized with our learned tokenizer, then it is getting padded. And how this padding is like? This padding is like this in the first context. I mean, the first run, basically. And you want 7 words, right? So the for loop will run for 7 times. So in the first loop, this is what you see. Okay, just the word of the Shiva. And with that, you are passing it through the prediction. Now, I say that the softmax is basically giving you a probabilistic prediction. These are the probabilities. Okay, and out of that you want the highest probability index. So the highest probability index is getting stored over here, which is 439. So the 439 index, if this index is matching with the tokenizer.word index that I was showing at the beginning of this project, if it is matching, then it will output that word. Exactly what we are getting is sub, matching to this index number when the token list was 2124, and this is the probability. Now if you want to check for yourself if it is a probability or not, you can uncomment this line and you can see the total probability score for every looping, and you will see this is coming as 1 or near to 1. Okay, the 100 percentage maximum. So in this is the first loop, this is the second loop. So this is the word of the sub that is getting appended, then the BTS that is getting appended, the best. In this way it is going on, and you can see over here that your token list is also increasing with this first number slowly moving to the left, and so your probability is also changing accordingly, and you are ready with your prediction. So along with Shiva, you have the sub which is coming after it in case of 2 gram, then the 3 gram BTS, then this is the complete sentence till you are ending up at 7 words. Okay, now if you give another word, it will give you a different kind of a prediction. Okay, so this is a very simple text generator, but yet very important to understand about the architectural process. Okay, so this is ending with our uh, project section. I will just show you, I'm not going to explain it in detail right now. We are not having that much of time, but I'm just going to show you how the CNN is like. Now, this is on my own system and I have a GPU. I ran it on a GPU. This is how this convolutional networks are looking like. So this LSTM network we have seen in the title generator that I will give it to you. In this case, of where is it? Yeah, convolutional neural network. When I say that you just have to use this conv2D and the max pooling layers, you do not have to perform any of this mathematics by hand. I meant that you have this kind of APIs available. So just like this LSTM layer, we have this conv2D layer, and this conv2D layer is corresponding to this first convolution layer. Okay, and followed by conv2D, there is a max pooling layer, and again this conv2D, again this max pooling, and I have used it this many times, and then applied the dense layer. So dense layer is the last layer that is getting applied with the CNN, with the RNNs also, right? And this is one of the example that I forgot to show you. This is for the global average pooling only that we did in the chatbot. When I said that it is doing the average out, this is a good representation of it. Okay, that you have this many numbers, or let's consider it as pixels, and you're averaging it out to this small stuff with all information, important information being retained. Okay, cool. So this is what it is. Now, I hope it's understandable ending the session with this. If you have any question, please to ask and I will answer that ROC AUC one. But before that, do you have any question regarding to this our session today? Okay, so there is no question related to it. I hope everyone have understood all of it. Okay, so since there is no question, okay. So getting back to that question on this ROC AUC score, I'll just draw it here itself. ROC AUC score is actually depending on the true positive rates and the false positive rates. Yeah. So it is depending on the true positive rates and the false positive rates. ROC, AUC, the full form is basically a receiver operating characteristic area under the curve. Okay. It is used for the classification purpose mostly, as I said. What it does, in case of classification, we normally do not use this accuracies. We do use it, but normally the accuracy tends to give us uh, the accuracy do not tend to give us the accurate results all the time. So we use the ROC AUC curve, which gives us the accurate results. How it looks like, the graph somewhat looks like this. This true positive rate goes along this y-axis and the false positive rate goes along this x-axis. And there is this kind of a line. The below area is the AUC calculation and this above area is the ROC calculation. Okay. And this is kind of a random classifier. Now, whenever you will plot the true positive rates and the false positive rates, making the graph, what does the terms mean? Okay, this true positive and the false positive rate, these terms are actually, you have to understand the confusion matrix in that case. Over here, these true labels and the um, predicted labels and the true labels, you have it something like this, and then you have this true positive rates, that is how much it has matched, and the false positive rate, how much the negative terms has matched. And after that calculation, you plot the true positive rates for the model and the false positive rates for the model, and from there you calculate this ROC AUC score, which has a formula for it, and you get a graph something like this. So the graph, more the upperwards it will go, more will be the better. And if your graphs comes out something like this, it is the worst graph. Okay. Now the concept is quite broad. Okay, so if you are unaware of this confusion matrix, I guess you have to start it from there. Uh, okay, so at first you need to understand the confusion matrix. I will tell you in a very short. Let's say I have something like this. Okay, let's say these are my predictions, drawing it over here, and these are my true labels, that is these are my output that I gave the model, and these are my predicted output that I'm expecting out of the model. And from here I see that out of, let's say, 100 positive values, that is 100 yes, let's, or 100 cat. Okay, 100 cat, it has successfully predicted 90 cat in the true positive zone. That means my model says it is 90 and my true positive values are also saying it is 90. So this is a true positive rate. And left over of this 10, my model says that this is cat, but according to this, my model says it is 10, but my true positive label says that it is not 10. Okay, so that is again a false positive rate. Then there is a true negative rate also. Like when my model is defining that this is, when there is something as a dog, and I, let's say it is 50, and my model says that this 50 are not cat. Okay, then what will happen, that my prediction value says that this 50 images are not cat, and my true value also says this 50 images are not cat, which is right, true negative rate. And the false negative rate will be 0. And then you pick up this true positive rate, false positive rate over here, plot it, put it under the ROC AUC score, and then you get it. Okay, so I'm ending it over here. I hope you have a brief understanding of what this is like. I'll go through this true positive rates and the false positive rates later on while doing the generative AI models, because we need to perform the classifications over there, and this will be coming in handy. And don't ask me for the formula, because this is kind of like integration. This is integrating it from in this area zone, this complete zone, integrating the true positive rates and the false positive rates as a function of it. So it's quite complex. Okay, fine. So ending it over here for today. I hope everyone is clear, since there are no more questions about it, and I hope you enjoyed this session. Yeah, over to you. Sorry if you were speaking, but you are not audible. Am I audible?
Hello, am I audible now?
Yes, you.
Yeah, yeah. Thank you, Nishi ma'am. So I hope like everyone's doubt is clear. So I think we are good to end the session now, and hopefully we'll connect in the next webinar. Thank you, ma'am.
Thank you. Bye, everyone.